Hi guys, this is the third video of the Dynamic Programming Algorithms video series, in which we focus on how to code dynamic programming algorithms in Python. In the second video, I introduced the shortest path problem and talk about how to solve it with Dijkstra's algorithm. In this video, I will talk about another algorithm, namely Bellman-Ford algorithm, to solve this problem. If you don't know what the shortest path problem is, I recommend you watch the previous video of this video series. First, let's recall the undirected graph that we used in the previous video. There are 6 nodes and several edges with positive weights. Also, let's recall the paths from node 0 to node 3 with path 0, 1, 3 being the shortest one. In the previous video, we showed that we can solve this problem by using Dijkstra's algorithm. Now, let's make this the graph directed by giving directions to each edge. For an undirected edge, we have 2 directed edges from one to the other. Let's do some modification on the edges. For example, let's remove the edge from node 3 to node 5, and then decrease the weight of the edge from node 5 to node 3 by 5.5 to make it minus 4.5. Notice that the shortest path from node 0 to node 3 becomes 0, 1, 4, 5, and 3 with length of 1. Now, just think for a moment if Dijkstra's algorithm could identify this path as the shortest one from node 0 to node 3. To find out, let's use Dijkstra function which we wrote in the previous video. Before running the function, we need to make some adjustments in the code. First, we need to change the way we construct adjacent nodes since the edges are not undirected anymore. To do that, we delete the second row in the for loop. Second, to obtain not just the shortest path lengths, but also the paths as an output, we initialize a dictionary called paths. The keys of this dictionary are the nodes, and the values are the shortest paths as list to the corresponding node. We assign the path of the source node to itself. Then, whenever we find a better path than the current one, we update both the path and its length. So we just replace this line with an if condition and the updates. Here, we don't change anything in terms of the logic. We just write things in a different way so that we can update the paths. Also, we modify the if condition to allow updates for only temporary nodes, which is in fact a part of the algorithm. Otherwise, we can obtain some cycles. We should have added this condition earlier, but we didn't, because when the weights are positive, no cycle is possible. Lastly, we return paths along with their lengths. Let's run this function for our graph. After modifying the inputs based on the directed graph, here are the outputs. For now, we just focus on node 3. Note that the shortest path from the source node to node 3 is 0, 1, 3 with length of 1.5. So we obtained what we expected. Let's decrease the weight of the edge from node 5 to node 3 and make it minus 4.5. We expect that the shortest path will be 0, 1, 4, 5 and 3 with length of 1. However, it's still 0, 1, 3 with length of 1.5. So, Dijkstra's algorithm fails when there is a negative weight edge, because the principle of optimality, which I explained in the previous video, does not work anymore. For such cases, we need to use another algorithm. For example, Bellman-Ford algorithm. Before explaining Bellman-Ford algorithm, here's some notation. S denotes the source node, and WUV denotes the distance from node U to node V. Also, dV denotes the length of the path from source node to node V. Lastly, the number of nodes is denoted by n. The algorithm basically relaxes each edge n-1 times because a path can consist of at most n-1 edges. In the first step, we assign the path lengths to infinity for each node, excluding the source node. For the source node, the path length is 0. In the second step, we iterate n-1 times for each edge and update the path length for the corresponding node as follows. This is the part where we use dynamic programming, so the recursion. Let's code this function in Python. The inputs and outputs are the same as in Dijkstra function. Also, as in Dijkstra function, we initialize path lengths and paths. Then, we iterate each edge n-1 times and update the current path if we find a shorter one. As we did before, we can return both the paths and their lengths. Let's run this function for our directed graph. When the weights are positive, we obtain the expected result. 0, 1, 3 is the shortest path with length of 1.5. When there is one negative weight, the shortest path is 0, 1, 4, 5 and 3 with length of 1. So it looks like it works fine. Before being so sure, let's do one more experiment by making the weight of edge from node 5 to node 3 minus 5.5. Now, the shortest path to the node 3 shouldn't change, but its length must be 0. Here are the outputs. Notice that the shortest path length is not 0. It is minus 1 instead. If you look at the paths, there is a cycle, namely 1, 4, 5, 3, and 1. And the weight of this cycle is minus 0.5, which is negative. So Bellman algorithm fails to solve the shortest path problem when there is a negative weight cycle. However, the good news is that it can detect negative weight cycles. Before showing how it does, it's worth mentioning that if there is a negative weight cycle, the concept of shortest path problem is meaningless. Because by moving through a negative weight cycle, the path length can become minus infinity. Let's go back to Bellman-Ford algorithm. To identify the negative weight cycles, we add another step as follows. The condition checks whether we can extend the current path. If we can, then the path should have n edges, which is not possible because a path can have at most n-1 edges. So there should be a negative weight cycle. We can easily modify the code to check this condition and let it print whenever it detects a negative weight cycle. In this video, using Bellman-Ford algorithm, I showed you how to solve shortest path problem in the existence of negative weight edges but not negative weight cycles. I hope that it was helpful. Please leave a comment if you have any question. In the next video of Dynamic Programming video series, I will talk about Floyd-Warshall algorithm for the shortest path problem. This time, we will find the shortest path between all pairs of nodes.